So welcome to lesson 3, where we're going to talk about common quantitative research designs. Most of the focus will be on experimental design, but we'll just do a brief overview of observational designs that we talked about in a previous lesson. So let's first look at the observational design and just review this that we talked about previously in this class. So, if you remember, observational studies only seek to observe phenomenon, not to influence them. So again, you may want to observe or want to describe a phenomenon, such as the amount of physical activity that children perform during recess. You're not actually influencing them or assigning them to a particular group. You're just sitting back and you're watching them in terms of their physical activity level. The researcher may think that an independent variable is statistically associated with a dependent variable, such as age and physical activity, and you want to observe or identify data that based on age, sex, race, demographics, and determine if potentially age is affecting the amount of physical activity. So these are some observational designs. Now in this class, unless you're doing a thesis that's been pre-approved by your thesis chair as outlined in the syllabus, you will be doing an experimental design. And the reason for that is the experimental design will use all aspects of the course that we've talked about. It also allows you to go a little bit more in depth into some of the critical thinking. So observational design certainly has their merit. In fact, usually they're sometimes the foundation of the precursor to experimental designs. If someone observes something and then they decide, you know what, let's go and maybe influence this and increase or decrease that an independent variable and see what happens on the dependent variable. So this is just an observational design and what it means. Now here are some common observational designs. The first is being a descriptive study, where data are collected from individuals at a single time point and only descriptive statistics are reported, such as you might report the percentage of individuals at a particular physical activity group. Those that are, those that are not. They may maybe age or weight. Does that have an influence on potential physical activity? But you would just report the mean, which is the average, and the standard deviation for that. We'll talk more about standard deviation later on in the course. Now, a cross-sectional study is when data are collected from individuals at a single time point and statistical analysis are run to see if two or more variables are associated. So example, let's say age and physical activity, as we talked about previously. You would have determined if there might be an association as one gets older, does their physical activity decrease or increase? And you would do some statistical analysis. Age would be the independent variable, physical activity would be the dependent variable, and then you just want to determine age and physical activity. Or it could be age and body weight. As you get older, is there an association with increased body weight? So that's a cross-sectional study. It can be used to help describe some phenomenon and maybe an association between two variables. The next design is the retrospective cohort study, where you look at data that's been previously collected from a cohort or group and are compared to data recently collected from their same cohort to see if two or more variables are associated. So for example, it might be individuals who smoke and lung cancer. So you would take a group of individuals that have lung cancers, and then you would survey and find out if they smoked previously. And then you would draw a conclusion, an association potentially between smoking and lung cancer. You obviously wouldn't randomize individuals to a group of smokers and then follow them over time. That'd be unethical, knowing what we know about the disease-causing aspects of smoking. But this retrospective cohort study will allow you to take data that's been previously collected and compare it to phenomena that's happening or data that's collected today or recently. And the final type of observational study is the prospective cohort study, where data are collected from a cohort at baseline and then again at multiple time points in the future to see how associations among variables change over time. So using the smoking analogy, you would take a group of smokers that would be currently smoking. You do some baseline measures about their overall health, and then you would follow them over a 10 to 20-year period and determine what their health outcomes would be. You wouldn't randomize these individuals as we talked about. You would simply just observe and find out if smoking led to various diseases. Another observational study, prospective study, would be physical activity and health outcome, measuring the various groups in terms of the amount of physical activity they do, measure what they're doing at baseline, and then you have them follow that group over time, over a 10 to 20-year period, for example, and determine if there was a protective mechanism of the amount of exercise and a decrease in health risk. So these are just some prospective cohort studies, examples, and they would fall under the observational design. So these are just some 4 different examples of observational design. Again, in this class for your research proposal, you won't be doing observational design, but it is important to have at least a understanding of how observational designs are performed in the different types. So now we're going to move on to experimental design, and this is the design that you'll be using for your research proposal in this class. So we're going to go over the details of the experimental design and some things to consider when using this experimental design. So just a review, we've talked about it previously, but just a reminder that experiments are used, design are used to explore cause and effect relationship between variables. Did one thing potentially cause another? Okay, so in other words, did eating a certain amount of type of food cause maybe potentially a particular increase in health risk, for example, or performing a particular type of resistance training, did that have an effect on muscle mass increase? Now, researchers typically assign a treatment or an independent variable, such in our case, resistance training, to some of our oral participants to see if it leads to a change in another variable, such in our case, it might be increase in muscle mass or hypertrophy as a dependent variable. And they want to determine is, does a certain type of resistance training, does that have an effect on hypertrophy, muscle mass? Now, the experimental design is used in a study is determined by the purpose of the study and the associated hypotheses and or research questions. So it's important that after you've done your review of literature, you start to come up with a research question or hypothesis, that once you have that good hypothesis of what you think might happen, then you need to design it appropriately to help answer the hypotheses. So that's going to be very critical. Your research design is going, and how it is designed and performed is going to be critical in your ability to answer your hypothesis. A poor research design will have holes in it and it'll have limitations and prevent the researcher from coming up with a sound determination of their hypothesis, if it was correct or not. So be cognizant of that in terms of your experimental design. So here, before we go on and talk about experimental design, there's some symbols that are going to be important for you to be aware of so you can understand some of the different research designs. When using the word, the letter R, that means random assignment to groups. So in other words, a particular group has been developed that has been randomized. The individuals have been randomized to that particular group. You have now an O indicates that a data collection time point, so that at that point, that is when the data was collected. X indicates the experimental treatment or intervention that was used during that period of time. And there is no symbol for control group, so it's represented by a blank space. Now let's go on to the next slide and talk about some examples. So here is 3 examples of the research designs. So, so due to the potential for pretest sensitization or testing effects, some researchers may use a post-test only design or a Solomon randomized four-group design. So just keep that in mind. However, let's talk about these examples here. The first is the pre-test, post-test randomized control group design. And if you remember, the R indicates that the groups have now been randomized to a group, that an intervention group, and and to potentially a control group. Here is an example of the data has been collected, and here is now the indication of this is the treatment group, and then we have now a space indicating that this group is a control group that may not undergo any type of treatment. After so much time, you can see now that these individuals, that there's another data collection period. There could be an example where now you would continue on. You could put an X here, followed by a space here, and then followed by another O here and here. What this would indicate would be like a repeated measure design, that over time, ever so often, you would be collecting data as the individuals continue on treatment, or followed by control. So this is a pre-test, post-test randomized control trial, where you basically randomize the individuals, you collect initial baseline data, one group has the intervention, another group has as a control group, followed by the data collection. So the other two tests are the post-test only randomized design and the Solomon design. And now, as I mentioned at the beginning of the slide, is that due to potential for pretest sensitization or testing effect would mean familiarization with with something. Some researchers use a post-test only design or a Solomon randomized four-group design in order to prevent maybe the actual test that they're doing at baseline that might influence what might happen at the end. And so a couple of ways to remove this is to use a post-test only randomized control group design, where they are randomized into the two groups, but then they do the intervention or they're the control group, and then their only data collection period is at the end. Now, the limitation of this is that it's difficult to know, potentially, is this just a continuation of what was already happening if there's no way to compare with pre-test data. Well, to get around this is they use a Solomon design, where you actually have two intervention groups, as you can see here, represented by the X, but one has baseline data and the other group does not have a baseline data. And they would do the same thing for the control group. Again, the idea behind this now is using this model, where you have baseline data for one group that's intervention and another group that has no baseline data for the intervention group. It then substantiates that if this group here, to avoid that testing effect, it allows you to compare that to this other group where you have baseline data to determine whether or not this is just continuation of what would already happen, or if there truly was an effect, but it would prevent you from having any type of testing effect that might have occurred. And you would do the same thing for the control group. And so the downside to doing the Solomon design is the fact that you basically double the size of your study, which can make it difficult for in terms of recruiting, and also increases the cost. But if it's important enough to remove potentially any testing effect or bias that might happen with the initial baseline data, this certainly is a design that you could use. Now, there may be situations where you need to do a pre-experimental design in order to collect some preliminary data for a larger study. However, there are some limitations to these pre-experimental designs that might be obvious, but let's discuss them. The one is you have the one group pre-test, post-test design. And the idea here is you just have one group where you do baseline data, followed by the intervention, followed by post data or post-test data. And the limitation of this is that without having a control group, you're not sure if there was any actual improvement that would not already have occurred compared to doing nothing at all. So there are some limitations to this design, but it would be useful if you want to collect some preliminary data that can be used in, let's say, a larger research design. Now, the one-shot case study design is where you take an individual where there might be have been doing some exercise or been doing something and um, over a period of time, and then you decide at the end that you're going to test them. An example of this might be students who come into a class, they go through a certain number of weeks of information, and then they're tested. Well, without having any baseline data on that information or any baseline test, it's not sure if if the student actually learned anything, or they may have already known it. So the limitation of this is not without a pre-test data, it's difficult to know if the intervention had as much of an impact. Now, some way to get around the one-shot case design is use a static group comparison design. And the way this would work is that similar to the one-shot, you would have that group where you would do intervention followed by post data, but you would add a second group where there would be no intervention, such as like a control group. However, the downside to this is that there was no randomization between the two groups. So one group may have had more intelligent or hardworking individuals versus the other group. And so it's difficult to draw any conclusions. And that's why over here, when we talk about the pre-experimental designs are not very useful for investigating cause and effect due to threats to internal validity, which I'll talk about in a little bit. So just there's just an example of some pre-experimental designs that are best really used for some preliminary data that might be used to design a larger experimental study. Now, another research design is called the quasi-experimental design. And they have similar properties as true experiments, but they do not involve random assignments to groups. So the first here is a non-equivalent control group design. And the reason you would use this is the fact that there might be situations where it's unfeasible, unrealistic to randomly assign groups. For example, if you have students in a particular area, you can't really randomize them to particular schools, a treatment school versus a control group. So you would have to actually do some statistical analysis in such a way to control for that. But the idea here is that you would do baseline data, and one group would be the treatment school, another group would not, followed by the follow-up data. Another example might be differences in gender between two groups. Instead of being able to randomize, it might be unfeasible to randomize individuals to groups between males and females, and so you'd have to make adjustments accordingly. And the idea is that the researcher then can control for any differences between the two groups and therefore provide a better understanding of the data. Another way is to control for the way that individuals were recruited in terms of trying to recruit as close to similar groups as possible if you're not able to randomize them. So that's another way to control in these non-equivalent control group designs. Another type of quasi-experimental design is the equivalent time samples design, also known as a crossover design. And the idea behind the crossover design is that individuals serve as their own control. So for example, let's say you had a supplement A and supplement B. And what you would want to do is you would have individuals take supplement A for a certain amount of time, then you would test them, and then you'd have a washout period. And then you would follow up with supplement B, determine the effects of that supplement. Now, the downside or limitation to this is that the washout period, the time in between that you allow the supplement A to remove or get out of the system may not be long enough. And so supplement A may be remaining in the individual system when they start the supplement B. And therefore, the results may indicate that from B might be more effective than it really is because it's actually being improved by supplement A. So a way to control for this or to have for this is to have a control group. Or if not a control group, you would want to make sure that you have ample time for a washout period between the use of sample A and sample B. And, and the other option is to randomly assign the order where you might have half the population begin with sample A and the other half begin with sample B. And this would ensure, hopefully, kind of tease out any of those issues or that might come up if you only use this crossover design uh, as we described with one sample A and then supplement B in that order. So it's best to kind of randomize them, the order with half the subjects at the beginning and half the subjects in one group at the beginning and the other half at the other supplement at the beginning. And then wait for a washout period and then switch the order, the supplements and who gets what. So anyway, these are some examples of some quasi-experimental designs. Again, they're not really involved. The limitation is there's no random assignments to groups. And so these are some things to be considered when talking about quasi-experimental designs. Now, there are some important considerations that when doing experimental designs. The first is the threat to internal validity. Well, what is internal validity? The internal validity of an experiment concerns how successful researchers are in controlling for as many, or if you're lucky, all potential alternate explanations for the effects of a treatment. So you want to make sure you try to control for anything else that might help, that might contribute to the outcome or explaining the outcome. So you want to eliminate that or reduce that as much as possible so you can, so the only thing left at the end of the study that might explain the changes that were seen was due to the experiment done. Well, what are some common threats to these internal validities? The first common threat is the history effect, or other environmental influences on the participants between pre-test and post-test. So if you're in a community, for example, and you're doing a particular intervention, well, there might be some kind of other program that's happening in the community that your participants are exposed to that might be contributing to the outcome. So it would be difficult for you to control for this, but it would be something that could affect the outcomes that have nothing to do with your treatment. So trying to prevent other environmental influences on the participants from the time they begin the study to the time they end the study are going to be very important. Another is the maturation effect, where the participants get older, smarter, wiser, et cetera, between pre-test and post-test. So for example, if you're using, let's say you're doing a longitudinal study with teenagers, and you're looking at the effects of resistance training on muscle mass gain, well, if individuals begin in pre-puberty and then during that study, if it's long enough, go through puberty, well, there's changes in hormones that might explain changes in muscle mass growth. So being able to control for this and prevent this is something that could affect your internal validity, for example. The next is the testing effect, which is whereas pre-testing can increase familiarity with the tests. Or what happens is by doing the baseline measures, the individuals learn what to expect. And then at the post-test, they know what to expect. And the changes are simply because they're familiar with what's happening. A common example is if you're going in and at baseline, you're doing strength, let's say a strength assessments on, let's say, a bench press. For example, if a participant has never done a bench press before and you go in and you start to measure them, they may feel unaccustomed to doing a bench press. And if you don't perform, if they've done it for the first time and their results may be very low, not because they were able to perform to their maximum, but because they hadn't done it before, they just were not able to lift as much as they normally would. Well, now over time, they perform the intervention and they come back after a while for post-test. And now they're familiar with doing the bench press. Well, now the increases in strength may simply be because they're more familiar how to do the bench press, not because of anything that the intervention has done. And so it's important to control for this. And one way to do this is to have a familiarity period where you would actually bring someone in maybe a week before actual pre-test, and you just familiarize them with, let's say, the bench press, how to do that, wait a week, and then you would actually have the pre-test. So the last is the instrumentation effect, where potential changes in the measurement procedure from pre-test to post-test may affect the outcome. So for example, let's say you wanted to test someone in body composition and you're using skin fold measures using skin calipers. What could happen is if you have someone, let's say person A, investigator A, were to do the skin folds at the beginning, but at the end you'd have a different individual would do the skin calipers. Well, you may get different results simply because the two individuals that were doing the skin calipers between the pre-test and post-test may have different procedures and their changes may simply because in how they actually assessed the skin folds. So in this particular case, a way to control for this is to ensure that the same individual would be doing pre-test and post-test, or to make sure that all the individuals doing the data collection are doing it correctly and doing it the exact same way. So these are threats to internal validity that you should be familiar with. Now, here are some additional threats to internal validity you should be aware of. The first is the Hawthorne effect, or the attention effect, where participants respond to the attention they are receiving in spite of or in addition to the treatment they are receiving. For example, if you're looking at there's certain types of drugs on treating depression, for example. Well, you may have an individual may simply respond who might be undergoing depression when they're receiving their medication because they're having more contact with an investigator that might be caring and more receiving of their concerns versus another individual who might be just receiving it with someone who may not be as nurturing or caring. So you need to be, this is called the Hawthorne effect in terms of the amount of attention that a individual or participant is receiving may be causing the changes as opposed to the actual intervention that you're doing. The next is the John Henry effect, where this is where participants learn that they are in a control group, which they perceive as, quote, inferior, and then they respond by trying to outperform the experimental group. So for example, let's say they're unaware at the beginning, they're in the control group, and so they get baseline testing, and then throughout the study, sometime they learn that they're in the control group, and so in order to not feel, quote, inferior, at the end, they go above and beyond what they normally would do in order to outperform, in their view, the experimental group. Well, this obviously is going to change the outcome because now the person is changing their behavior, not what they normally would do, but simply because now they know they're in one group versus the other. The next is the demand characteristics, where participants become aware of the expected outcome of the experiment, and then they may try to please the researcher or sabotage the experiment. So for example, if they're trying to please somebody, um, they understand, let's say they're in a resistance training program and they know that they're supposed to increase muscle mass or um, have increase the strength. So the individual will then try to do additional things, maybe outside of the treatment, let's say an extra day of resistance training, or do certain types of things they normally would not do in order to please the researcher. On the other hand, they may sabotage the experiment because they don't agree with potentially the outcome might be. And so they may not try as hard, or may not do what they're supposed to be doing. And this could actually cause the experiment not to be as successful as it would be had the person not been aware of the outcomes. So in this case, it's important for the individual to be blind to what the outcomes might be, if at all possible. The final is contamination, where participants in the experimental group interact with participants in the control group or another intervention group, and then they discuss the details of the intervention protocol, which may influence the behavior of the control group or another intervention group. So for example, if the intervention group and control group are starting to intermingle and one's telling the other about what's happening, well, that may then affect the behaviors of both of them, and that could control that as opposed to what they normally would do. Or you could have a multiple treatment groups, A and B and C, and just one control group that has standard of care. Well, if they're all intermingling outside of the lab setting, well, that may end up changing the behaviors of individuals that compared to what they normally would do had they not known what other groups were doing. So all of these are internal threats to validity, and it's important to be aware of them and try to control or prevent them from happening as much as possible. And this goes into proper research design that we'll talk about before a little bit later in this class. So the next thing to consider is the external validity, which is an experimental concerns how accurately research can generalize their findings of the research study to the population the sample was taken from. And so many research are concerned a lot with their internal validity, but sometimes they may not be effective at preventing external validity, and their generalizability of taking the findings from the research study to a larger population is limited. Well, there are some common threats to external validity you should be aware of. The first is selection bias, where the lack of random selection or random assignment of participants can at least partially explain effects of treatments. So, for example, if you have, let's say, a group of individuals you're measuring changes in strength increase, well, you could have a group that might potentially have more individuals who have more experience in resistance training versus those who do not. Well, and therefore, individuals with more training experience may have the knowledge to increase their strength versus the control group. And essentially, that was the explanation, not because of the actual intervention you were doing. The other is reactivity to experimental setting, where the findings in an experimental setting may not transfer to a natural setting. So a lack of translation. So you might be using a setting or an intervention or where you're at may not be realistic to the general population at whole. The other is reactivity to testing. So pre-testing may increase sensitivity to the experimental treatment. So, for example, if you're working with your population, well, they're going to be exposed to the pre-testing, whereas in the general population, they're not. So having that exposure to the pre-testing may affect the outcomes, unlike what would happen to the general population. They may not have the exposure to the pre-testing. The other one is the multiple treatment interference, where presenting participants with multiple levels of treatment may not be reproducible in a natural setting. So, for example, let's say you take a supplement and you gradually over time increase that supplement over a certain amount of time, and then you measure the impact that might have on the outcomes to find the most optimal dose that would have on that outcome. Well, in the general population, the individuals would simply just go to the optimal dose, but they may have side effects because they didn't have that gradual increase in dosage that prepared them for the optimal outcome. And so this is an example of where the individual would then be exposed to some, not have the most effect. And so they needed control for that and to avoid external validity. There's also something to be aware of called confounding variables. In experimental research, a confound is a variable that affects both the independent and dependent variable and was not accounted for in the experimental design or statistical analysis. For example, if you're doing a study where you're doing the effect of lean body mass, the independent variable, on the basal metabolic rate, the dependent variable, well, the individual, the investigator, may not have accounted for age that might influence both of these. Well, another example might be comparing males and females in terms of driving and the number of accidents. But something to consider is, for example, is the amount of time that males may increase the amount of driving time versus females. So the increased chances of them causing an accident might be due to the fact that they drive more versus, say, the females, as an example. So not controlling for the amount of time driven, for example, could cause you be a confounder in terms of understanding your results. So unless you control for these confounders, it's going to make it difficult for the individual to determine the actual outcome. Or there's some potential solutions to confounding. So to increase experimental control by identifying potential confounders a priori or before the study begins, and then controlling for them in the experimental design. So most of the time that can be taken care of through participant recruitment procedures as well as the experimental protocol. For example, if you, let's say you want to determine the effects of supplementation on muscle mass growth, for example, you would want to make sure that you would have individuals who are not taking any other supplements. And so in your um, procedures to recruit, you would want to make sure you tease out individuals that might be taking additional supplements that could be the explanation for the um, changes. And also, let's say you want individuals with similar maybe training experience. And so you want to have a confounder, which would be maybe the amount of time individuals or experience that people have. So if you took an individual that has no experience with resistance training and then someone who has 10 years experience and you give them the supplement, well, it could be years of experience might be the changes in terms of what you see in muscle mass, and has nothing to do with the supplement you're taking. So to control this is you would want to have individuals with similar training experience, for example. Well, another way is that along with experimental group, use attention control groups, where one control group gets attention and another control groups gets no special attention. And the idea behind this controls any type of attention bias that we talked about in that drug study and depression. So this kind of takes away or teases out any effect that attention might have on the outcome of the study. The final and one of the most effective ways to prevent confounding is using placebos and blinding. For example, a double-blind placebo control group so that neither researchers nor participants know who is receiving the treatment and who is receiving the placebo. An example would be, let's say you're doing a various type of new drug on the treatment of preventing cancer. Well, in this particular case, the individuals, the subjects or participants would both would be taking a pill. One would be a sugar pill, and the other would be the actual intervention drug. But the participants would be unaware of who's getting the sugar pill and who's actually getting the drug itself. And likewise, the investigators would not know who is in what group. They would not know who was in the control group and who was in the drug group. And the idea behind this is it prevents the investigator, if they knew ahead of time which group they were in, then they may provide more attention to the group that's receiving the drug and not as much attention to the group that's receiving the sugar pill. And the idea behind keeping both of them blind is then individuals will not alter their behavior, and the investigator would not alter their behavior and their interaction with the participants. And this really ensures to determine is, in this particular case, is it the actual drug that's causing an improvement, or is it just a placebo effect where someone is thinking that they're on a drug and therefore, wow, they must see an improvement. So by keeping individuals blind to both the treatment that they're receiving and also the investigators of who is in what group, it ensures that any effect that the drug might have is due to the drug itself and not the fact that the participants were aware they're taking the drug or the fact that the researchers were aware they were taking the drug, and both would change their behavior. So these are confounding is a very important thing is to control for and prevent. So the outcomes that you're looking for in a research study are only due to the intervention that you are using in the study. So keep that in mind as both the threats to internal and external validity and any of the confounders to make sure that you have a solid research design. So this concludes this section of lesson 3. Make sure you have a good understanding before you go through and take the quiz.